Okay, moving on, we're going to cover chapter 9 in our textbook on policy prediction with approximation. Okay, so we're finally done with tabular methods that have their limitations, as I'll show you in a second. I'll show you an example of why they are so limited. And we'll start discussing function approximators. And later on we'll see how these can be incorporated in clever algorithms to really get us some nice behaviors, nice policies, general policies. One might say actually learn nice behaviors. Okay, so far we saw tabular methods. Tabular learning keeps a table of all state values, right? But in realistic situations, we cannot possibly learn about every single state. There are too many states to visit them all during training, and too many states to hold a value table in memory. So instead, we want to generalize. That is, we want to train on a small number of states from experience, or some manageable number of states, and then to generalize that experience to new similar situations, similar states. This is a fundamental idea in machine learning, of course, beyond reinforcement learning, also in supervised learning and also in unsupervised learning. So let's look at an example. What do I mean? So let's say that we're trying to train a reinforcement learning agent to play Pac-Man. And let's say that we discover through experience that this state is bad. Right, this specific state where Pac-Man is at this corner here, and the two ghosts are closing on it in this corridor. In naive tabular learning, we know nothing about this state. So you see this state, the new one here in the middle, it's a very similar state to this one, because again, Pac-Man is stuck somewhere in the corner and the two ghosts are closing on it. But the state representation, if we represent the location of Pac-Man and the location of the ghosts and the location of the food pallets, it's a different state, right? So that entry in our large table has no value assigned to it. We never saw it before. So we know nothing about this state, or even this state, right? If we have a very, very similar state, here at the left, a very similar state, but it is ever slightly different. We don't have that. How is it different, by the way? Can you see? No? Look at the top right corner. Right.
Dark missing.
So yeah, we're missing one food pallet right here. It's a different state. Now you might say, oh come on, it's practically the same state. Well, you know that with your brain. You're saying, I mean, from your experience, it's almost the same state. But for a computer, it's a different state, it's a different entry in the table. And this entry is empty as opposed to... So that entry is empty, but this entry is not. Meaning that our RL agent knows nothing about this state. And of course we want to fix that. We want to be able to generalize knowledge. And this is actually a problem. So let's say our state is the location of Pac-Man and the location of the dot and the location of the ghost. And you can see that naive Q-learning, after 50 training episodes, is not able to perform very well. Why? Because it never saw most of these states, right? The state changes once one dot is eaten, or the ghost moved to a position, all of the exact combination of Pac-Man location, dot location, and all of the dots location and the ghost location, if it didn't see that, it knows nothing about that state. Okay, so obviously this is something that we want to address, right? We want a more clever training approaches. So we want to learn an approximation function, either for a state value, V, or for a Q function as Q. The approximation function, we place a hat on it, right? It's just an approximation. For this example, let's just say that we're trying to learn a state approximation function. So it tries to approximate any state given as a parameter, S, and it has a set, so the semicolon is a common notation in supervised learning to represent a trained function. And after the semicolon, we have theta, which is the set of tunable parameters. So before the semicolon is the input parameters, what we feed to our function. And after the semicolon is the tunable parameters. So for instance, if we're training a deep neural network, these will be the weights and biases, for instance, okay? And our function for each state will return some value. This will represent the state value, okay? So what we would like to have is to train these tunable parameters for our function, such that for a given state, a state that we observed, and some observed value for that state, we are able to train our tunable parameters to output the same value for the same state. But we want our function to also generalize the knowledge and be able to predict states that it never saw before. Based on what? Based on features. Based on high-level features like the ghost location, Pac-Man location. I would like you to understand that being stuck in a corridor where you have two ghosts closing on you is bad, regardless of the exact location that it happens, right? So, of course, the more alike the state is, the more alike the prediction should be. But again, we want it to be able to generalize to the more abstract states. So indeed, let's see what happens if we use Q-learning with function approximator. This is a simple function approximator, a linear approximator. We won't go into that, we'll define that later. And this is a simple approximator. And we can see that once we have some very simple high-level features like the distance from the ghost and the distance to the dots, it is able to learn very efficiently with, again, the same 50 episodes that we've seen previously, right? Because it learns high-level abstract state representation that is helpful for it to learn to perform its task.